Have you ever really thought about the science packed into the safety features all around us? You know, from the airbag in your car to the simple padding in a shipping box. Well, there's some seriously cool physics at play. And today, we're going to dive in and uncover how these devices pull off what really feels like life-saving magic.
Okay, I know. It sounds like the beginning of a really weird joke, right? But believe it or not, the answer to this question, it holds the entire key to understanding how we survive impacts. We're going to come back to this, so just keep that egg in mind.
So before we get back to that egg, let's talk about something we've all felt. You're on a bus, maybe just standing there, and the driver suddenly slams on the brakes. Your whole body just lurches forward. That feeling? It's not just annoying, it's actually the very first crucial piece of our physics puzzle.
Right, so that lurching feeling is caused by a property of matter that, honestly, you could describe as just plain stubbornness. In physics, though, we have a name for it: inertia.
Here's the deal. Objects in motion really want to stay in motion, and objects at rest want to stay at rest. If you're moving at 50 kilometers an hour in a car, your body wants to keep going at that exact speed. It just naturally resists any change.
And this takes us right back to that bus ride. When the bus takes off from a stop, it moves forward, but your body's inertia tries to keep it right where it was, so you feel like you're thrown backward. And, of course, when the bus stops suddenly, the vehicle stops, but your body wants to keep right on moving forward. That feeling is inertia. You're feeling physics in action.
And this is where it gets really important: mass. The more massive an object is, the more stubborn, the more inert it is. Just think about it, right? It's way harder to stop a big, heavy bus than it is to stop a tiny taxi, even if they're going the same speed. That's because all that extra mass means a whole lot more resistance to change.
So, how does all this inertia stuff relate to an actual collision? Well, now that we've got a handle on inertia, we can bring in two more huge ideas that really explain the science of an impact: momentum and impulse.
The easiest way to think about momentum is as an object's unstoppability. It's this combination of how heavy something is, its mass, and how fast it's going, its velocity. So a heavy bowling ball rolling kind of slowly could actually have the same momentum as a light baseball that's been thrown super fast. Okay, so if momentum is the unstoppability, then impulse is what you need to actually stop it. Think of it like a shove, and the power of that shove depends on two things: how hard you push, that's the force, and for how long you push, that's the time.
The cause and effect here is actually pretty simple. First, you apply an impulse, that force, over a certain amount of time. That force changes the object's velocity, and since we know momentum is tied directly to velocity, you have now changed its momentum. Simple as that.
And there it is. Seriously, this is the single most important relationship when we talk about the physics of collisions. An impulse is equal to the change in momentum that it causes. You got to remember this one because it is the secret to everything that's about to come next. Okay, time to finally get back to our egg. We're going to solve the classic egg drop experiment, and when we do, we'll unlock the exact same secret that makes airbags work.
So just picture it. You drop an egg. In scenario A, it smacks into the hard floor and, well, it shatters. Splat. But in scenario B, it lands on a nice soft cushion, and it's perfectly fine. Why? What is the actual physical difference here?
Now, get ready for the really weird part. The egg starts with the same momentum and ends with zero momentum in both scenarios. This means the total impulse, that total change in momentum, is exactly the same whether the egg breaks or not. I know, it sounds wrong, but it's true.
So if the total impulse is the same, what gives? Well, it all goes back to the two parts of impulse: force and time. See, the hard floor stops the egg almost instantly. That's a huge force over a very short time. But the soft cushion, it extends the stopping time. By making that time part of the equation bigger, the force part can be much smaller and still add up to the same total impulse. And that lower force is what saves the egg.
This one simple idea, stretching out the time of an impact to lower the force, is the absolute genius behind so many of the safety devices we completely rely on. Let's take a look at a few. Airbags, car bumpers designed to crumple, highway guardrails that bend on impact. They all act just like that cushion for the egg. Their entire job is to increase the collision time, which drastically cuts down on the peak force that hits you,
or the object being protected. It's the exact same idea behind bubble wrap, the soles of your running shoes, and those giant mats that gymnasts land on.
Now, just when you think you've got it all figured out, there's a little bit of a twist. A seat belt, maybe one of the most important safety devices ever invented, doesn't really work based on the cushion principle. It's tackling a totally different problem.
So here's how these two things work together like a team. The seatbelt's #1 job is to fight your inertia. When the car suddenly stops, it's what holds you in your seat and keeps you from flying forward. But you still have to come to a stop safely, right? And that's where the airbag comes in. It deploys to give you a cushion, increasing the time of that final impact and dramatically, beautifully softening the blow.
Phew! Okay, so we've covered a lot of ground here, from lurching on a bus all the way to saving eggs. Let's just wrap this all up with the key things you really need to remember.
So look, if you take away anything from this, make it these 3 things. First, your body's inertia is that stubbornness that a seatbelt has to fight against. Second, an impulse is that combination of force and time that brings you to a stop. And third, the big secret, is that to survive that impulse, you have to spread it out over more time, just like an airbag does. So the next time you see a boxer rolling with a punch, or a stunt performer falling onto a giant airbag, or even just the bubble wrap inside a package, you'll actually see the physics at work. It's this simple, elegant principle that's quietly keeping us safe all the time. Makes you wonder, what else around you is secretly a physics lesson just waiting to be discovered?